Hi and welcome to the video lecture series on Wear Modeling and Simulation in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the second part of the video lecture and it is devoted to adhesive wear. Let us begin with adhesion. So adhesion is attraction between the molecules in two adjacent bodies. It is not to be confused with cohesion, which is the attraction between molecules within the same material. And this is depicted here in figure to the left schematically in 2D. So we have two bodies, 1 and 2, and the molecules are gray, colored gray in one and white in the body number 2, and they attract each other in some way, which means that if we try to slide them in that plane, there will be some resistance to that motion. On the right, and to the right, we have these two measure gauges from a set of many of them, and one is for 30 millimeter and one is for 10 millimeter. And as you can see, the surfaces that they contact with now are blank. They are mirror blank, which means that the roughness is extremely low, and when you put them together you have all possibilities of creating adhesion, as there is the same material in both bodies, and the molecules in both bodies, they will come very near to each other without being. Another way of looking at adhesion is at the gecko's feet. So, and this is a nature solution to adhesion, which is built by these small nano fiber-like structure, which on some micrometer scale looks like very plain fibers, but then if you zoom in even more, you see that the tips of those fiber has a nanostructure, and it is this nanostructure that makes the gecko feet stick to almost any surface. And this has been mimicked by carbon nanotubes, and this guy is called the GeckoBot, and in this paper that I give reference to here, they are discussing the development and fabrication of the actual fibers, so the adhesive feet of this GeckoBot. And it turns out that this gecko wall interaction, it can be analyzed by approximating these spatulas, as they call these fibers, as a long cylinder with a radius r, and then the interaction with a single of them and the surface is given by this integral, which is over all space, and it can actually be computed, and there is an analytical number given here, and you can find more about this in the paper, of course. We can measure adhesion in an AFM, and this can be done by lowering the cantilever towards the substrate, and as it adheres we can then try to raise it up and measure the force and measure the distance it takes for it to release. And in the middle up here you have a picture of different states of adhered cantilevers. Of course, you can try to model this by means of simple beam theory, or simple, but for example in the paper 1 down here by Fang et al, they employ the Wojnowski and Krieger beam theory, and it's a geometrically nonlinear beam theory, and they have the equations governing its motion using Lagrangian mechanics, and because of this the potential and the kinetic energies can be described as they are here on the right, and then we can use this to model the adhesion of that microbeam. So adhesive wear occurs when surfaces slide against one another, and the mechanism is that when the adhesive forces of the interface are strong enough to break loose a particle from the subsurface, we can observe wear of it. And the image here below, it illustrates two-body adhesive wear, and the sliding direction is from south to north, and the image is taken from Dr. Joel Furestig's PhD thesis from 2014. Let us look into the modeling of this adhesive wear type of mechanism. And one way of viewing it is that material adheres to the surface, and then wear may result from tensile and shear stresses within the contact zone and in the substrate. And you have a schematic picture of this here, showing an asperity made out of soft material, and it's moving, and we have this adhered material in pink. We have a hard counter body, hard material in the counter body, and we can see approximate sizes now because of if this is a asperity, it can be approximated by a certain radius, and therefore we can have an approximative Hertzian contact zone A, contact radius A, and also we know that the maximum stress will occur at approximately half of A, and perhaps it diminishes quite a lot down to A there, so therefore typically size of material could be looking like this, or a material that's affected by this and of the stresses in the substrate. And if this asperity now moves a certain distance, so we look at the next time step, which is 2a over v, and where the v is the sliding velocity of this asperity, then perhaps a wear particle has been taken off the asperity, and we have wear. Now it's time to look at the ARCHARD wear equation for adhesive wear, which is derived based on the following assumptions. So we consider this pair of colliding asperities, and they are loaded against each other under a small normal load delta W, because there may be many here that carries the total load, so the sum of all those delta V is the applied load. And then an almost Hertzian contact is formed, and we can define its radius as A, and therefore the contact area is proportional to A squared, so that this small contact area delta A is proportional to A squared, as we see here. So after sliding one contact length to A, the asperity then with the one asperity with the lower hardness, so the upper one in this case, may lose a particle, and we assume that that particle has a depth A. If we assume that, we're gonna get a volume which is delta V proportional to A cubed, so semi-spherical volume. And actually, if we like, we can express this in terms of the area as A times the area, approximately. I mean, now this is not a spherical one, that would be a rectangular slab, but or a cylindrical slab, sorry, not rectangular, slab of volume. Okay, so we move one contact length to A, and this cylindrically shaped or spherically shaped small delta V volume wear particle is loosened from the softer material, in this case the upper body. However, for this to happen, the asperity must be subjected to full plastic yield, so the contact pressure everywhere must equal the hardness of that softer material, and here we denote that with H. And by applying Newton's first law as force equilibrium and force balance, we have that minus delta V, if y is positive upwards, must be balanced by plus hardness times the area of the contact. And this means that delta V is H times SA, but since the volume or the area is related to the Hertzian radius A, we can reformulate this and say that delta W is proportional to the hardness times the small wear volume delta V over A, which is the Hertzian radius. So we have this expression meaning that the wear volume is proportional to sliding length and load and inversely proportional to asperity hardness. Let us continue with the second assumption. So we consider two rough surfaces with a myriad of colliding asperities, and we assume that each of the sliding asperity contacts causes a wear particle. So in addition to this, we also assume that no new contact forms during the sliding of the full contact length 2A. In this case, which is very hypothetical, the wear volume of the surfaces per sliding length 2A will be the sum of the volumes resulting from all the colliding asperities at a given time. So mathematically speaking, we have delta V indicated for sliding length 2A here, which is the sum then of all the asperity delta V's, and by means of what we had before, we can express this as sliding length times the sum of the loads over the hardness, and that becomes in the end the total applied load, of course, because the sum of the loads that each asperity carries is the total applied load. So we have delta V proportional to A times the load over the hardness, and here we have used capital delta to declare that the volume delta V is generated from all the wear of asperities and during the small sliding distance 2A. So next up, still considering two rough surfaces with a myriad of colliding asperities, but we also realize that the previous concept of having no new formation of wear particles during the sliding length of the contact is pretty hypothetical. So now we assume that it may form a new wear particle before the previous is fully lost, and with this we we include now an a priori unknown probability for this wear particle to appear, and we denote this with K. And now K is the unknown probability for the formation of a wear particle as the surface slides the distance delta S. So now we have also deviated from the sliding distance 2a, because during now delta S there may be a probability K that a wear particle is formed, and this means that the wear volume delta V per sliding length delta S is the sum of all the volumes resulting from colliding asperities times the probability for the formation of a wear particle. So now we have the sum delta S delta V over H times the probability K. And again we can move the sum, and we have K delta S sum V, which is just K delta S V, which is the applied law, over H. We note that on the left hand side we have delta V per sliding length delta S, and on the right hand side we have K delta S W over H, but there is not an equality between these two expressions. It's a proportionality. So let's now try to transform this proportionality into an equality. And this may be done by defining an adhesion wear rate, and this may be done by the nomenclature introduced here. So K subscripted adhesion is now the wear rate, which we may determine, or which is usually determined experimentally, and it is a system property, and it encompasses a lot of things, among the probability of a wear particle to be formed, and all those many other things, or many of those other things, are actually listed in section 6.1 in the compendium, which tells you this story, that it can be the materials, due to the composition of the material, the microscopic shape of the bodies in contact, machining marks, the topography of the contacting surfaces, and the type of lubrication and the lubrication regime that the contact operates in, ambient conditions, humidity could be, temperature, and so on. So it's all of this in combination that leads to this wear rate coefficient denoted K adhesion. Now with this, the wear volume delta V per sliding length delta S at a given time could be expressed as we see here, and this is precisely an ARCHARD'S law for adhesive wear. And moreover, if we can assume that during delta t, or during time t, if the wear behavior is not changing, then we can express the wear volume in terms of the sliding length S, the total sliding length S, like this. There are some interesting publications on modeling and simulation of adhesive wear, and here we see a molecular dynamics type of simulation model for the AFM tip and the adhesion at the AFM tip. So on the left we can see an AFM tip, a real one, and a gold substrate, and we can also see the model of this by means of molecular dynamics. To the right we see two stages of the tip sliding on the substrate, and we can see how the friction force increases as the tip adheres to the substrate. And it's also noted that you have a sort of a blend of material at the tip, which is also deformed then at the second state. So this was it about adhesion, and next up will be abrasive